CCI, Crash Course Instrumentation, presents Episode number 64. Ground isn't magic, your zero is a choice. Cold open. Sea level is not a tool you carry up the mountain. It is a reference everyone agrees on. Ground in a circuit works the same way. Choose it, measure from it, and your readings make sense. Viewer promise. By the end, you will explain ground in plain English. Read single-ended and differential measurements with confidence, and use split supplies without getting lost. Quick bridge from episode 63. Last time we walked the loop. Sources felt like rises, loads felt like drops, and the loop balanced. Today, we choose where zero lives, so our meter numbers tell the right story. Section 1. What ground really is. Ground is the point we call zero, so every other voltage has meaning. It can be a copper bar, a chassis, a power supply terminal, or a drawing symbol. Choosing ground does not change the circuit's behavior. It only changes how we describe voltages. Think of ground as your ruler's zero mark. Move the zero mark and the numbers change, but the distance between 2 points stays the same. Section 2. 2 ways to read with a meter. Single-ended reading. Red lead on a node of interest, black lead on ground. This tells you how high or low that node sits compared to zero. Differential reading. Red on one node, black on another node. This tells you the difference between the 2 points, with no need to involve ground. Say it out loud as you probe. Node to ground or node to node. Your words guide your hands. Section 3. Split supplies. Plus, minus, and ground. Many instruments and control loops use plus, minus, and ground on the same supply. From plus to ground, that feels like a rise. From minus to ground, that feels like a drop from ground's perspective. From plus to minus, that is the full difference of the two. Your choice of ground sets what the meter shows, but the story stays consistent if you keep track of direction and reference. Section 4. Bench Mini-Lab. Move the reference, not the truth. Set up a supply with 3 terminals, plus, ground, and minus. Add a simple series load so current flows. Measure plus to ground, say rise. Measure minus to ground, say drop. Measure plus to minus, say full difference. Now move your black lead to a new zero. For example, tie black to the minus terminal, and repeat. Notice how the numbers change, while the differences between nodes tell the same loop story. Pro tip, sketch a tiny ruler in the corner of your notes with plus, ground, and minus marked. Your notes become your compass. Section 5. Common grounding confusions. Confusion. Ground equals earth. Reality. Sometimes the chosen zero is Earth, but often it is just a local reference on a floating supply. Confusion. All grounds are the same. Reality. Signal ground, power ground, and chassis ground may be connected in one place only. Multiple connections can create noise or shock paths. Confusion. Clamp the black lead anywhere metal. Reality. Confirm the actual return path. A painted panel or an isolated bracket is not a ground. Confusion. Differential equals dangerous. Reality. Differential just means you are measuring between 2 arbitrary points. Respect energy, pick safe points, and keep one hand away from the circuit. Section 6. Field checklist. You can use today. Define one ground for the drawing you are using. Mark that symbol on your sketch or tag the bar in the panel. When numbers look odd, ask, who chose zero here? Try a differential reading to double-check the story. Before adding jumpers, confirm whether grounds are already tied somewhere else. Speak the words rise, drop, difference, and ground every time you move the probes. Tiny historical note. Early telegraph and telephone systems often used earth return as the reference. Later, metallic returns and carefully placed single-point grounds reduced noise and made measurements consistent. The lesson stands. The choice of reference changes the numbers you read, not the physics. Tease for the next episode. Next up, real-world KVL, hospital EKG leads, aluminum smelter, movable ground, and everyday appliance faults. Same loop law, bigger consequences. Call to action. If this clarified ground for you, please like, subscribe, and share it with a classmate or a coworker. Credits. Thank you to Tony Coupalt and the open source community for the model materials that make Crash Course Instrumentation possible.